Safa, ele é físico pela Universidade do Texas, Texas University, right? Ele está fazendo o doutorado dele na Universidade de Wisconsin-Madison, nos Estados Unidos. E hoje ele vai falar alguma coisa sobre, né, os neutrinos e também a participação que ele tem na colaboração do IceCube. O IceCube é uma grande colaboração, acredito que ele vai falar um pouco. Well, thank you, Ibrahim. Thank you very much to coming here and to allow to talking. And if you want to start the webinar.
Great, thank you, Douglas, for the invitation. And I will, today I'll talk to you a little bit about neutrinos and what we can do to solve two of what I think are the big mysteries that are still standing in our understanding of the universe. And so the outline of my talk will be as such that there's basically two unsolved mysteries where neutrinos can play a major role. The first is the origin of cosmic rays, and I'll talk about that extensively in a second. And the second is the nature of dark matter and whether it has a connection to the Standard Model. And so I'll begin by discussing cosmic rays, and cosmic rays were discovered in the early 1900s by Victor Hess, who you can see here was landing one of his balloon flights. And so what Victor Hess did is he took an electroscope and flew into the atmosphere trying to measure the radiation as a function of altitude. And the understanding was that, you know, the radiation was coming from the Earth. And so as you go higher, the radiation would drop. But what Victor Hess discovered was that the radiation was coming from above. And this is what we now call cosmic rays. It's charged nuclei that are coming from space. They're mostly protons, but they could also be anything up to iron. And they have energies that go all the way up to 10 to the 20 electron volts. Now, for reference, you know, the energies that we've been able to achieve here on Earth with accelerators is about 10 to the 12. So you're looking at about 100 million to 1 billion times higher in energy than we can achieve. And so there are three very interesting questions here. First is, where are they coming from? The second is, how are they able to be accelerated to these very high energies? And the third is, what source types are responsible for different portions? So you see the spectrum has some features. And so it is believed that different parts of the spectrum are caused by different sources. So this on the plot here is the flux versus energy. And this flux is dropping very fast, but it goes all the way up to 10 to the 20 electron volts. And we think that there are several types of sources that are responsible for these different energies of cosmic rays. Now, the hard part about answering the first question, which is where are these cosmic rays coming from, it's hard to answer because cosmic rays are charged. And so when they're traveling through the intergalactic medium, they get deflected by magnetic fields, which is, you can see here is the dashed line. So eventually when the cosmic rays arrive at Earth, their direction is completely random. You cannot point them back to any location. Now, gamma rays, which we've used for astronomy for quite some time, are electrically neutral, so they don't have that problem. But gamma rays love to interact. And so on their way to Earth, as you can see denoted here, they produce an electron-positron pair, for example, which decays back to a gamma ray and then, or annihilates back to a gamma ray, I'm sorry. And then you eventually get gamma rays at Earth, but they're at lower energies, and if they interact enough, they might get diffused, so they don't directly point back to the source. The source has become extended, and the information basically is lost from the source of acceleration. Now, neutrinos, the reason neutrinos are the perfect messenger here is because they are both neutral and they don't like to interact very much. They only interact via the weak force, which means that they can travel all the way from the source of acceleration to Earth without ever interacting. And so they are the perfect tool to discover the sources of cosmic rays, but at the same time, these advantages also make it really hard to even detect neutrinos in the first place because they cannot interact very much. And so to detect neutrinos, you need something such as the IceCube experiment. And what I show you here is this picture taken at the South Pole. This is the IceCube lab. And the sides here, the poles are basically all the cables that are coming from below the ice that transfer the data into this data center, and then it gets transferred via satellite to Madison. And so this is a schematic of IceCube. The building I showed you is shown on top here. And basically, the concept of IceCube is, you go about 1 kilometer deep into the ice where there is no source of light that can exist outside of subatomic particle interactions. And so we drill these holes, about 86 holes that are 2.5 kilometers deep. You put 5,000 or 5,100 basketball-sized light detectors that are spaced about 17 meters vertically and 125 meters horizontally. And so you instrument 1 billion tons of ice, and you look down and just wait for light to show up. And you know that this light has to be coming from a neutrino interaction because nothing else can make it through the Earth except for neutrinos. And for scale here, I looked up the tallest building in Paraíba, and it's the Tour Genève. And if you can see it, I put it there just so you can have some perspective. I mean, I sometimes forget how massive this detector is. And so IceCube completed construction in 2010, and it's been taking data since then. It took about, I would say, more than 20 years since planning to deployment to completion. And what we're aiming for here is to detect the highest energy neutrinos. So this plot here, I show you the flux of natural sources of neutrinos versus energy. And I'll just walk you through some of them very quickly. So that at the lowest energies, between 10 to the minus 6 and 10 to the minus 3 electron volts are the cosmic neutrino background, and that is basically the leftover neutrino radiation from the Big Bang. It's a very high flux, but the energy is so low that we have yet been able to detect this flux. There are experiments dedicated to detect such a neutrino flux. None have been successful so far. There's the solar neutrino spectrum, which comes from the fusion at the center of the sun, and this was used to actually confirm that fusion was the source of energy in the sun back in the 50s. Before that, it wasn't quite certain. The terrestrial neutrinos are neutrinos created from radon and uranium or thorium and uranium that's left in the Earth, and that has been detected. There's supernova 1987A. As you know, more than 99% of the energy of a supernova is emitted in neutrinos, and so these are usually very high fluxes. But in our galaxy, they only happen about once per century, and so everyone's waiting for the next one. The atmospheric neutrino flux. Now, this is where we get to the region where IceCube is sensitive. IceCube is mostly sensitive to neutrinos of energy 1 giga electron volt and higher. And so those are atmospheric neutrinos created by interactions of these cosmic rays that I just talked about. So these cosmic rays come to Earth, they smash into the atmosphere, and then as part of those interactions, they create neutrinos as well. And so we're able to see those neutrinos regularly. Then there's the higher energy neutrinos. Those are labeled AGN and GRB. Those are theoretical models. We don't yet know what exactly the sources of the neutrinos are, but we know that they're coming from outside of our galaxy. And and they have energies above a peta-electron volt, which is 10 to the 15 and higher. And so these are the neutrinos we're after. And as part of the science project of IceCube, we can do astrophysics, neutrino physics, earth sciences, dark matter, and BSM physics. Now, this is a lot of topics that I will not cover today. I will focus mostly on neutrino astronomy and then indirect searches for dark matter. But if you're interested in any of these other topics, feel free to contact me, and I'll point you to the right papers or people who are working on these things. And so essentially what IceCube sees is just blobs of light. We have a bunch of, like I said, basketball-sized light detectors, and we can see either tracks, which are caused by, these are muon neutrinos, and so neutrinos come in 3 different flavors, and depending on the flavor, they create a charged particle that corresponds to that flavor. So a muon neutrino will create a muon, an electron neutrino will create an electron, a tau neutrino will create a tau. And so these colors here represent time, so it goes red to blue, and so you can just follow the rainbow. And as you can see, we see hits as a function of time, and we see more hits in certain places than other places, and that's denoted by the size. So the bigger the bubble, the more charge was deposited in that region. So a track is basically a muon neutrino that is created in muon, and the muon can then is relatively long-lived. It can go through the detector and leave a track of light. And that's really good for astronomy because it gives us very good angular resolution. But because the event is not completely contained inside your detector, we don't have very good energy resolution. So it's about a factor of 2 energy resolution. On the other hand, the cascades are created by either neutral current interactions. So those are interactions where the neutrino just exchanges a neutral Z boson and then just exchanges some energy and is not converted into a charged particle in the process. And these cascades deposit all of the energy inside the detector. So we have very good energy resolution, about 15%, above 100 TeV. But as you can see, it's hard to tell where it's coming from. And so the angular resolution is a little worse. And then at the higher energies, you have something that is called a double cascade. So one flavor of the neutrinos, the tau neutrino, can create a tau lepton, and the tau lepton doesn't live very long as much as the muon. And so if that happens inside your detector, you will see the tau track and then the tau decaying. And so what you'll see is these 2 distinct cascades very close to each other, and that we call a double cascade, and we've actually observed the first few candidates of that, such an event. Now, again, to put these events in perspective, I took one of the highest energy events that we've detected and superimposed them on the Asude de Wadokongo. I hope I said that right. And as you can see, these are massive scale events, just so you can get some kind of idea. All right. So I will now talk a little bit about the astrophysics. So there are several ways that we have detected or measured astrophysical neutrinos. One of which is just, like I said, by looking through the Earth. So if you look down, you essentially block all the backgrounds because nothing else can make it through the Earth. So I show you here in this little drawing. You know, when cosmic rays interact, they create a bunch of charged particles, and those are blocked by the Earth. And then all that's left are these neutrinos. And then when they interact either inside or near your detector, you see the muon track coming from that interaction. And so essentially what it means is that if you see an upgoing track, you know it has to be a neutrino. Another advantage of this method is that because you are certain that anything coming from below is caused by a neutrino interaction, this gives you an extended volume that is outside your detector, and it increases your effective volume. So the muon range is about 10 kilometers at 100 TeV to 1 PeV. And so you're effectively increasing the volume of your detector by looking at any muon that comes from below. And so this is the measurement that was made. I show you here results with 9.5 years of data, and we see an excess of high energy neutrinos. So as you can see here, the data, if you look at the plot that says truncated energy, you can see that the neutrino energy goes all the way from 100 GeV up to 10 or 10 to the 7 GeV. And the purple line shows you the atmospheric neutrino flux, whereas the red line shows you the astrophysical neutrino flux. And you see it's quite clear from this picture that you have an excess above the atmospheric neutrino background, and that turns on above 100 TeV. And so this flux here has a spectral index of about 2.3. And like I said, it's been seen in several different channels. Now, you can characterize the spectrum, and then you can use these muons to ask the question, where are these neutrinos coming from? So in order to do that, we can talk about how these neutrinos can be, or these cosmic rays can be accelerated to these energies. And so there's no thermal process that exists that can create these energies. And so what you need to convert some potential energy into kinetic energy. And the sites that we know of that have the highest possible concentration of energies in black holes, and those have extreme gravitational wells, and they can provide this acceleration if they convert some of this gravitational energy into acceleration for the protons. Now, these protons get accelerated, and then what you do is you have, let's say, a target matter or target radiation. So that can be either, this black hole sometimes is accreting matter or is eating up stars. And so these can be the targets for your protons, and then these protons would hit the matter and then produce neutrinos as a consequence of these interactions. So as you can see here, I highlight the P gamma and PP interactions. And so those interactions will create pions and kaons, and those pions and kaons will decay to neutrinos. Now, in 2017, we began sending out alerts to all of the other telescopes that look for electromagnetic sources. And this particular alert was interesting because it was an upgoing muon track. It was coming from below the horizon. It had an energy of about 300 TeVs. And as soon as we sent out this alert, a bunch of telescopes followed up. The first couple were the Fermi Gamma Ray Satellite, which I show here. And the Fermi Gamma Ray Satellite saw that there was a source called TXS 0506 that was within 0.1 degrees of this event. And the source was flaring. The flux from the source was about 6 to 8 times higher than its normal emission. And so many other telescopes followed up, and even I show you here MAGIC, which is an experiment that looks at much higher energies than the Fermilat can do, because Fermilat is in space and they're limited by the size of which they can get a detector to space. But MAGIC is an Earth-based telescope, and they can detect about 100 GeV gamma rays, and they saw the same signature they saw a flare that's coming from that direction. And the chance of that happening randomly was ruled out at the 3 sigma level. So this is a quite interesting event. It's not necessarily a discovery, but it's interesting. And it was it triggered this huge multi-messenger follow-up by all of these telescopes that I show you here. There's about 11 or 12 telescopes that followed up, and this was published in a couple of papers 2 years ago. Now, more interestingly, once we figured out that this location is interesting, we went back and gathered all the data on tape and looked for a neutrino emission that's coming from this source previously, before the alert. So this plot that you see here showing the hold on, let me. So as you can see here, this would be the alert that we saw in 2017. And then we found another flare of about 13 neutrinos back in 2015. That is a very strong flare with a very hard flux, and the background hypothesis was rejected at 3.5 sigma. So then the question becomes, can you connect that observation to the 2017 observation? And the problem here is that there was no gamma ray enhancement seen at the time that we saw this big neutrino flare in 2015. So the plot I show you here on top is the flux in photons as a function of time. And the time that we saw the neutrino is highlighted in orange, the band in orange, and the straight dashed line here. And so, as you can see, while there was a tremendous activity in 2017 when we saw the alert, in 2014-15, the source was relatively quiet. And so this becomes hard to reconcile. How can you have both of these consistently? And then Halzen et al. In 2018 showed that if you want to have an efficient neutrino source, a source that emits a lot of neutrinos should be opaque to gamma rays, exactly due to the requirement that you need a target matter. So if your protons are hitting a lot of material, the gamma rays will interact in that material, and they will not make it out of the source at energies that are high enough to be detected by, let's say, for example, the Fermi-lat or MAGIC. And so what you need here is you need a major accretion event. You need a lot of material falling into an active black hole to explain this 2014 event. And this is in fact true, because if you look at the radio observations of TXS, here I show you on the bottom right, the radio flux is a function of time. So we found out that TXS is not your typical blazar. And then these people here, Britson, Fent, et al., proved that this source was flaring in radio for years before we saw the flare, and during the 2015 events. And so radio emission is normally correlated with major accretion events. And so this fits the story very well. This was a black hole that had a jet, and then there was a lot of material falling in. This could be caused by galaxy mergers. So this could be two massive black holes that are rotating around each other. And as you know, when galaxies are merging, there's a lot of matter that's falling in, and then that could very well explain this phenomenon. Of course, that was just a single observation, but the more interesting part is that we saw this again. And so in August of last year, we sent out another one of these alerts, which you see here on the right. This event had also around a couple hundred TeVs. and it was followed up by several telescopes, and there was a source in the vicinity of the event called PKS 1502 that was observed to be at the highest radio flux density in its in the time that we've ever been taking data from the source. And so this source has been flaring for years, very steadily increasing, and it follows this narrative very well that the sources of neutrinos could be these very massive black holes that have a jet accelerating protons, and then a ton of matter that's falling into these black holes that would then cause the protons to interact and create a flux of neutrinos that we see. So I will summarize the usual picture here, which is the origins of cosmic rays are unknown. Neutrinos are ideal messengers because they point directly back to the source, and they are the key here to solving this mystery. IceCube, of course, with the help of the entire observational astronomy community, has finally shed some light on this cosmic ray mystery, and there are further searches ongoing to search for neutrinos specifically from galaxy mergers. This has not been done, but it's work that's ongoing right now. So now that we've talked about the typical explanations for the origins of these neutrinos, we can move on to some more exotic explanations. So again, the nature of dark matter is still unknown, and its connection to the standard model. And so I like to liken this to, again, when I was looking up Campina Grande, I was reading some mythology, Brazilian mythology, and this caught my attention because it was an apt analogy here. The Cobra Grande was historically associated with areas of the Amazon that were still unexplored, and so anywhere that was unexplored was thought to be occupied by this big snake. And the story was that the snake would lure fishermen in, and of course, kill them. And in this analogy, the Amazon would be the standard model. The Cobra is the dark matter, and I, unfortunately, am the fisherman. So dark matter has been unambiguously observed, at least its gravitational effects. We've seen, I'll give you several examples here, why we know dark matter exists and why we think it has connections to the standard model. So this picture here is showing on the left the visible light. And as you can see, a lot of these galaxies are warped and they're lensed. And that happens when you have a lot of matter in between you and the source. And so the light gets warped on its way to you. And on the right, you see a fit. The halo here is a fit to the best matter distribution that would describe such a lensing. And as you can see, the areas where there's a lot of clumps of these, the blue clumps, don't line up with areas that we think that we see galaxies or stars. And so this is the first sort of clue that there's matter that we cannot see, but that is there, and it's bending light that is on its way to us. Another evidence for dark matter that's observational is rotation curves. And so this is here a measurement of the speed of star systems around the center of a galaxy. And from Keplerian laws, you would expect that as you move farther and farther away, the speed should drop. And so this is the expectation that you see here in the dashed line. Just based on what we see, what we infer, the amount of matter that exists from the starlight that we see. But the observation says something completely different, and that is almost the speed not only is flat, but it tends to even increase somewhat in some galaxies. And so this tells us that there is matter outside of the visible matter that we see. that is causing these systems to rotate much faster than you would expect. Another sort of piece of evidence is the cosmic microwave background, and this is the strongest piece of evidence that we have, and that is depending on how much matter you put in at the beginning of the universe, you will get different. So structure can either form or it cannot form. You need to have seeded very high dense areas in the universe such that matter can accrete on those regions and then form galaxies, which is what we see today. But if you have no dark matter, we know that galaxies cannot form. And if you have too much dark matter, we know that the galaxies as we see them today will not form. And so if you put in exactly the right amount such that it also lines up with what we think is inferred from the rotation curves and from the lensing measurements, everything works. And so this is very compelling evidence that there is dark matter and that it might be connected to the standard model. The reason it might be connected to the standard model is that we've seen, for example, I show you here the bullet cluster. And so the bullet cluster is a famous galaxy merger where there are two galaxies that are going away from each other. And so you can see here in red, these are the visible, or not necessarily visible, but light measurements. So this is X-rays and gamma rays and visible photons. And so these two galaxies had just merged and they're moving away from each other. But then when you look at the distribution of matter that is in that galaxy from lensing observations, you see that blue distribution there. So most of the matter has decoupled from the visible matter that we see after this collision, which means that this cannot be a gravitational effect. If this was modified gravity, you would not see such a decoupling of dark matter from matter as these galaxies collided. And so the consensus here is that, based on this observation at least, is that there is some portion of matter that is weakly interacting. This dark matter has to be at or lower than the weak scale, and it could be connected to the standard model via some new dark force. And so how do we typically search for dark matter? So what we do is essentially, we introduce this mysterious new dark force that I denote here with a cartoon of Darth Vader. And you can do it several ways. You can either shake it, which means you build a huge detector on Earth. We know that there's a flow of dark matter in our solar neighborhood. And then you wait for this dark matter to hit one of your nuclei in your detector, and then when it hits it, it shakes a little bit, it recoils the nucleus, and then if you can measure that recoil, you've discovered the dark matter cross-section. Another way you can do it is you can make it. So you have colliders, of course, and that's how we've discovered almost all of the standard model particles in the modern era, such as the Higgs and the Z and W bosons, is you just accelerate protons to very, very high energies or electron-positron pairs, and then you collide them, and then you create resonances at the mass of the particle that you're looking for. And so if the dark matter exists at some mass, you can just look for a bump in the spectrum of your collisions. And then what this talk will focus on is the break it part, which is in this scenario, you just look for a source of dark matter naturally, and then you wait for standard model particles to come out of it. because as we know, every particle that we know of, except for the electron and the proton so far, tend to decay to more stable states. And from the CMB measurements, we know that the dark matter, if it's a weakly interacting massive particle, should also decay or annihilate. And then some of these decay or annihilation products could be standard model products. And so you look and you wait and you see if you have an excess of standard model products coming from the direction of places where there's a lot of dark matter. And so why is looking for annihilation to neutrinos interesting? Well, if you stop and think about it, dark matter can decay into any standard model product, but eventually the stable states that will reach Earth are either going to be photons or neutrinos. And so searches for dark matter with photons have come up short. So we have not discovered dark matter using photon observations yet. There are no compelling excesses of photons anywhere. And so the only thing left is decay or annihilation to neutrinos. And because neutrinos are so hard to detect, these neutrino fluxes that are coming from dark matter could be present but undetectable as of yet. And so if you assume that dark matter decays or annihilates 100% of the time to neutrinos, you get an upper limit on the dark matter annihilation cross-section to any standard model products. So again, it is more powerful to look for dark matter. That's more constraining to look for dark matter through photons. But since these searches have not shown anything significant, the only avenue left for this model of dark matter is annihilation to neutrinos. And this is motivated by some gauge invariant models. You can have natural models that show that dark matter can decay or annihilate primarily to neutrinos, and that way you can escape the bounds on dark matter from photons. And so the flux of neutrinos from dark matter annihilation can be coming either from our own galaxy or from outside the galaxy. And so from our own galaxy, we know that there's a halo of dark matter at the center of the galaxy. And if that halo undergoes annihilations, we can compute the flux of neutrinos coming from there. And that flux, d phi dE, will depend on a few things. One of them is this is the thermally averaged dark matter annihilation cross-section. So this is the quantity that we're after. There's the neutrino production spectrum. So this is the energy spectrum of the neutrinos that you expect from these annihilations. And in this case, we just consider direct annihilation to neutrinos. So 2 dark matter particles give you 2 neutrinos, and that is just a delta function. And then there is of course, you have to account for how much dark matter exists between you and the galactic center. And so this is called the J factor. And so all it is just an integral of the dark matter density over the line of sight, and then it's integrated over the solid angle. And so you just count the dark matter particles between you and the galactic center. And you can use several different profiles to parameterize your dark matter distribution. What we use here is a data-driven fit to lensing and rotation curve data. And so these rotation curves, like I explained before, tell you the difference between a galaxy without dark matter and a galaxy with dark matter. And so you can fit for the distribution of dark matter that would give you these measurements. And so this is the profile that is used in that paper. Another contribution from all of the other galaxies, apart from our own, can also be computed, and that's the extragalactic contribution. So you expect that every other halo in the universe will also annihilate and give you neutrinos, and these neutrinos will make it to you. And so now you're not only integrating over the density of a single halo, but you're also integrating over the distribution of all halos as a function of redshift. And this is, I will not go into too much detail here, but all you're doing is you're redshifting your neutrino energies, as you see in the red box here. Now your flux is dependent on the Hubble parameter, so you have to account for the expansion. And there's also this extra halo boost factor that I said includes the contribution from all of the halos as a function of mass and redshift. So there are several parameterizations to this halo boost factor. And I show you here 4 different ones. And we use one of the more recent parameterizations, but we also include uncertainties on these fluxes. But of course, to find dark matter, first you must detect the neutrinos. And lucky for us, there's been a huge boom in experimental neutrino physics in the last 2 decades. As you can see here, early in the 50s, in the late 50s and the early 60s, there were just small neutrino detectors that were aimed at discovering the neutrino and then discovering the solar neutrino. And then as time goes by, we're starting to first develop more technologies, such as you see here, the Cherenkov technology, and using natural bodies of ice and water has allowed us to really take the active mass of the detectors up to levels that using other technologies might be cost effective. And so detectors such as Hyper-K, IceCube, and others are enabling the search for these very high energy neutrinos from dark matter. And so, of course, there are many, many more neutrino detectors that we can use to ask whether we can find signatures of dark matter in them. And I list here some of them. It's not an exhaustive list. For example, Borexino is an experiment in Gran Sasso, Italy. It measures solar neutrinos. I think it's about, I show it here. And then Camland is a reactor neutrino experiment. But of course, it measures neutrinos from nuclear reactors, but it can also see extraterrestrial neutrinos. Antares is the concept of IceCube, but in water. And it's undergoing an expansion now to have about the same volume of IceCube. And Pierre-Auger is a cosmic ray detector, but it's also sensitive to neutrinos at the highest energies. These are 10 to the 18, 10 to the 19 electron volt neutrinos. And then there's next generation detectors such as DUNE, which is a liquid argon TPC. It's a beam neutrino detector, but it's also sensitive to atmospheric neutrinos. CTA is a gamma ray detector, but it will also be sensitive to gamma rays that are emitted at the highest energies. Neutrinos radiate, of course, and you can detect the gamma rays coming from neutrino radiation. And then there's Tambo, which is an experiment proposed in South America. It's a cliffside water Cherenkov detector, and it's aiming to measure the astrophysical tau neutrino flux. It will be about 30 times bigger in effective volume than IceCube. So that's very, very exciting. And it should be, it's proposed now, and it should be, hopefully if it's funded, should be built in the next 10 to 15 years. And then there's GRAND, which is a big radio detector proposed to be built in China. And that will also hopefully detect EEV neutrinos. So this is the expected neutrino flux from dark matter, shown as a function of energy for different dark matter masses. And so blue, orange, green, and purple are just the heavier and heavier dark matter masses. And I plot them here on top of the atmospheric neutrinos in the left plot and the top right plot. Those are atmospheric nu mu and nu e fluxes that Super K and IceCube have detected. And on the bottom right is the astrophysical neutrino flux as detected by IceCube in 7 years of data. And so you can use any of these detected fluxes to look for this dark matter. And as I've explained, there are other experiments there as well. And so when you put this all together, this is what you end up with. This is now the result of this work that I'm linking here. And so this is an annihilation of dark matter into neutrinos as a function of dark matter mass. And as you can see, you can use Borexino at the lowest energies, Camland, Super K, and in the future, Juno. And then at the highest energies, of course, IceCube and its counterpart in the Mediterranean, Antares, take over. And then you have next generation proposals such as Tambo, the next generation of IceCube, KM3net, and Dune and Hyper-K, which will also get closer and closer to the thermal relic abundance. Now, the thermal relic abundance is, as I explained earlier, the amount of dark matter required in the early universe. If it has a cross-section that is explained by this line, it fits all of the measurements. And so if dark matter exists, it fits all of our observations, and it annihilates the neutrinos. The cross-section that it should have is this dotted line. And so as you see, we're getting really, really close to finally probing the region where we can rule out or discover WIMP models where dark matter goes to neutrinos. And so this is just a focus on the lower energy side. As you can see, the most interesting part here is at 30 MeVs, where we're basically, I would say, flirting with the thermal relic abundance. And then at the highest energies, as I explained, Auger and Tambo, and then the Anita, which is a balloon experiment at the South Pole, can also make such limits. And then I will skip over these because of time, but I will summarize that the nature of dark matter and its connection to the standard model are still open questions. We have a lot of clues, but there's nothing conclusive. As we know, neutrinos are the first chink in the standard model armor. So we know that there has to be new physics in the neutrino sector. We know that neutrino masses cannot be explained by the standard model, and neither can dark matter. And if we can combine these two problems into a single solution, that'd be great. And so searches for dark matter in the neutrino channel is a necessary complement to searches via charged particles and photons. And so here we've updated the existing limits and derived new ones all the way from MEV to ZeV. And then the next generation experiments will finally dip their toes in the thermal relic abundance region. I will take your questions now. Thank you.
Well, thank you, Ibrahim, for this very didactic presentation. Well, a lot of information here. Ok, some question. Vocês podem falar também no chat se quiser fazer em português, a gente pode traduzir.
Hi, I'd like to make a question to Ibrahim, please.
Ok.
My question is about the IceCube. That the IceCube is a tool to find the higher energies about neutrinos only, or that IceCube has another objective to find? It's just very energy, or there is some like that radiations or something like that.
Well, if I understand it correctly, you're asking what other objectives can IceCube, what other things can you use IceCube to detect? And I would say that astrophysical neutrinos is the is the worst thing that we can detect. So we see only about 10 astrophysical neutrinos every year, but IceCube sees about 1 million atmospheric neutrinos every year. It sees billions of muons coming from the atmosphere, and so you can use all of this data to do many different things. We do neutrino oscillations. We search for sterile neutrinos because you have some interesting effects through the Earth. We even have people who are only interested in ice because the ice properties are so important for us. They are basically our biggest uncertainty. And so we have glaciologists who all they do in IceCube is just study the ice because there's so much history down there. This is ice that has accumulated over tens of thousands of years, and so there's interesting science there. And then there's you can look for Lorentz invariance limits, things such as monopoles and axions. Yeah, I'm not sure if I answered your question, but
yeah, it's more clear now. And I would like to ask you again about is there are there more tools to find neutrinos with I'm thinking the word uh, are they tools possible that we can find the neutrinos more easily on the university, or just the IceCube? There more? Are there more?
You're asking if there's better ways or other ways to find neutrinos?
Yes. Yeah.
Yeah. So I explained it very briefly, but I can go over it more. So the problem with neutrino detection is that you need very, very large detectors. So with IceCube now, this is 1 billion tons. So this is a lot of mass, and so the trick is you need to use things that already exist instead of building your own detector. And so that's what IceCube started. IceCube basically said, let's use Antarctica because this ice has already been there for tens of thousands of years. All we need to do is drill some holes and use the ice. So that's much cheaper to make this such a detector. So you can think of other ideas such as, like I said, Tambo. Tambo is thinking of using the mountains in Peru. So the Andes are a perfect target for neutrinos. And so the rock will provide you enough target to make the neutrinos interact. And then you can put detectors just on the side of the mountain and then look for the radiation coming outside of the mountain to detect the neutrinos. So you have to think of things that already exist, like mountains, volcanoes, Antarctica, a lot of ice, a lot of water. There's definitely better ways to do it than what IceCube is doing. There's probably cheaper ways to do it. Yeah, and you just have to come up with an idea that is applicable and cheap, and people will build it.
Okay. Sorry for my English. Thanks.
No, thank you. It was a great question.
Other question? Can you put at the IceCube detector slide, please?
Yes, of course.
I think the IceCube was a figurative, but in fact, it's ice. You don't use water, liquid. What difference is water and ice on the Cherenkov production?
Yeah, so actually the reason that we needed to put this in the South Pole is because this ice was really, really clear. And you cannot build this ice in a lab. So it's just caused by, pressure over tens of thousands of years that has made this perfect crystalline structure of ice. And so what this gives you is a very long attenuation length. So actually this string spacing of 125 meters was selected based on the attenuation length. So this is the length at which a photon can travel in the ice before it gets absorbed. And if you've done any measurements of photons in any medium, you'll know that 120 meters is something that's exceptional, right? So in water, this length is about, it's less than half. I think it's about 40 or 50 meters in water. So what putting it in the ice buys you is that you can space your detectors farther away from each other, so it makes it cheaper to build. But in water, the scattering length is much longer. And so that's the length that a photon will travel before it scatters, not necessarily absorbed, but scattered. And so this gives you better resolution. And so in ice, that's about 40 or 50 meters. And in water, that's about 80 or 90 meters. And so, it's a game of what matters to you more. Do you want a detector with high resolution, but more expensive? And probably harder to maintain because everything in water is moving. Or in ice, you would just drill some holes, put them in there, and you get a cheaper detector, but the resolution will be a little worse.
Oh,
can you
okay.
speak?
Can you continue?
I was. Did you show it to us a picture of a study of Budakongo, right?
Yes, right here.
Did you do any research here?
No. I was just looking up. I saw this this beautiful lake, and I thought it would be nice to show how big these events are relative to things you would see normally.
I thought did you do any research here in Paraíba?
No, unfortunately no, but I would like to. I would like to once this pandemic is over.
You are very welcome here.
Thank you very much.
Ibrahim, there is a question in the chat.
Oh, okay.
You.
Okay. Yes, I'm not quite familiar with this research, but it is an active topic even at IceCube. So you can solve this problem. This person is asking about. I'm guessing the handedness of neutrinos, right? Is this what I gathered? And so it seems that neutrinos only have a single. So you can solve this problem by assuming that there are other neutrinos, heavier neutrinos, right-handed neutrinos, and those are hypothesized. They're searched for. Nothing's been detected yet, but they would solve many problems. They're even candidates for dark matter. They cannot be all of the dark matter, but they can be a portion of the dark matter. And so if you have these heavy neutrinos, they would either decay or interact and produce these left-handed neutrinos that we see. But I'm not very familiar with that area of research, so I'm sorry if I can't answer that question any better.
Ibrahim, I have a question.
Sure.
Well, first, thank you so much for your presentation. It was a really nice presentation about this topic, and the figures about Paraíba and Brazil was also a nice touch. And well, I would like to know if you are, or if you know, if there is some experiments today which are mapping neutrinos using data from these gravitational waves events, or correlating the data or appearance of gravitational waves with appearance of neutrinos.
Yes. Yeah. So LIGO sees colliding black holes, colliding neutron stars, and neutron star black hole mergers, right? So those are the three basic events that they see. We have someone here actually in this building who does this analysis of trying to correlate neutrinos with gravitational waves. So what we do is we have an agreement with LIGO, and they send us their sky maps as soon as they have an event, and then we look at our data, because we have also real-time data, and we see if there's any neutrinos inside the contours of the gravitational waves. And that is not expected to happen in black hole mergers. It is expected to happen in neutron star mergers, because there's supposed to be very strong magnetic fields, and that can cause some acceleration and give you high energy neutrinos. So we've done this analysis. Unfortunately, LIGO has only seen 1 or 2 neutron star mergers. The rest of them have all been black hole mergers. So we did not expect to see anything, but we did the analysis anyways, and we didn't. Recently there was this electromagnetic counterpart to a neutron star merger, and that was very interesting, and people are still following up on that. But there were no neutrinos coming from there. We're hoping that, O3 was the third run of LIGO was stopped because of the pandemic as well, and so they weren't able to complete their data taking. But we're hoping next time they will be at their full sensitivity, and they expect to see dozens of these neutron star mergers, and hopefully, I would say in a couple of years, 2-3 years, we'll be able to pinpoint the first joint neutrino gravitational wave source, which should be very exciting.
Nice, thank you. And well, I have one more.
Sure.
About the neutrino flux, when you were talking about astrophysical neutrinos, I realized that in that formula that you presented, the flux depends on the actual value of the Hubble parameter H0. And nowadays, I don't know if you well, probably you were aware about it, but there is a crisis about the value of H0. So I'd like to know if you are aware about it, and what different kinds of flux you may expect if you change you have a considerable change in the value of H0.
Right. So while we were writing this paper, the tension grew, and we checked. So I think the values are somewhere between 67 and like 74 or something.
Yeah.
Kilometers per second, and it makes a very small difference. It's less than 5% difference in the flux of neutrinos from dark matter, but it makes a huge difference for any cosmological model, So it doesn't really matter for this work, but I think it's a very interesting piece of research that people should follow, because there's also this recent papers that are talking about the omega lambda can be 0, and so that also changes everything else, because they're reanalyzing supernova data. And they found that you can explain supernova data without needing dark energy. But the funny thing is that dark energy was proposed because of the supernova data. It was the most compelling piece of evidence. So now people are going back and saying, can we use the circular argument of dark energy has to exist because of the supernova data, and the supernova data can show that you can make these measurements without needing dark energy. So yeah, this is I just put that number in and I get the flux. Other than that, I don't ask too many questions. Yeah.
Okay. Well, if I can just put one more, there was a picture that you showed of the detection of a flux. I guess it was in slide 23, if I remember properly.
This guy?
Yes, this one. And I realized that there are a huge amount of little dots here in the base of the detector, but you have some small dots here in the upper part of the detector. And what is the difference exactly in the detection process when you have these few dots here above the detector?
Right. So this data is filtered. So if you look at the detector without filtering it, it's full of these little dots, because you have noise from the PMTs, you have muons coming in from the atmosphere all the time. But what we do is we send this data through a bunch of filters, and these filters try to causally connect these dots. And so it will say, we know that a muon goes through the detector within 1 microsecond. So anything that is not within 1 microsecond of the first big hit is then thrown out. And then you say, I require that, this hit is correlated with that hit in time, and so any of the other dots, these are left because they're probably occurring at the same time that the muon was going through, but they're just noise from the PMTs, so the PMTs just have random thermal noise.
Oh, okay.
Yeah.
Thank you so much for your answers and for the presentation.
Thank you for the great questions.
Okay.
I'd like to do the last question, if possible. I promise it's the last question. About CMD, cosmic microwave background. You told it was, but I didn't understand very well about this topic. Can you explain to us, please? It's about CMD.
Yes. Is this what you're referring to?
Yes, that's correct.
Yeah. So we measure photons that are left over from the Big Bang, right? And that's about 300,000 years after the Big Bang. And if the universe was completely isotropic, you would see no fluctuations. You would see the same signal everywhere in the sky. But what we measure is that there's different, so there's fluctuations in different parts of the sky. So there are certain regions that you see temperature differences in the CMB background. And so these temperature differences can be measured, but there's also models that can predict these temperature differences based on what the Big Bang, what happened during the Big Bang or right after. And so, there are very basic ingredients. You have matter and radiation densities. And so the amount of matter will tell you, so if you think of, if dark matter exists, it's the heaviest thing. And it's the thing that holds the kind of the universe together, and then the photons escape first because they're massless. And so if there's regions where there's more dark matter than other regions, you can imagine that these regions will have the fluctuations I'm talking about. So there are regions that will have more dark matter. There are regions that will have less dark matter, and that will cause differences in the spectrum of light that comes out in the early universe. And so how much dark matter you put in tells you a lot about how much differences you see. And so if you put in no dark matter, as the universe expands, there's not enough overdensities such that galaxies form. So there will be no structure. Everything will just be washed out. But if you have dark matter, then these are the regions that will be dense, and then that's where the matter will fall in, and then galaxies will form around those regions that have dark matter. So there's a direct correlation between these measurements of the fluctuations of the temperature that we see in the CMB and how much matter has to exist in the early universe such that you will get these fluctuations. Now, I'm not a cosmologist, so it probably wasn't a very good explanation, but essentially, you know, it's just, you're just playing with how much matter you need such that, you know, the temperature of the light that comes out will be a certain, will have a certain fluctuation.
Okay, it's better now, and that is an interesting and comprehensive subject to study, neutrinos. I think it's very hard to study to me for a while, but I would like to thanks to you for you and congratulations for your work.
Thank you. And if you guys have any more questions about not just this work, but you know, if you have questions about what it's like to work in neutrino physics in big collaborations such as IceCube, or what fields of neutrino physics, subfields of neutrino physics you want to go into, feel free to email me.
All right. Thanks.
Thank you.
Some question?
Hi. So firstly, thanks for the nice seminar. And I have a question. Since we have a very high energetic neutrino flux, we can have a kind of electroweak correction. And in this kind of electroweak correction, we can produce like charged particles, and discharged particles can produce also gamma rays, right?
Yes.
So it's possible to use this kind of gamma ray flux from this secondary annihilation in order to constrain some dark matter models and what we can expect from this.
Absolutely, yes. That's definitely true, and that happens above TeV or so. And what you get is, you know, that's why CTA here is relevant for our work, because CTA is a telescope that looks for gamma rays in the atmosphere. But if the dark matter is at very high energies here above a TeV, then the neutrinos it makes will radiate gamma rays. And so this here, this gray line, is the limit that you can set from this radiation. This was not explored very heavily in this work, but this was already done by Quiroz et al. And you can read their paper inside. It's referenced here, but it's a very difficult calculation. But you know, telescopes such as Fermi and Hess have already placed such limits, and like I said, CTA in the future will be able to place limits as well. So I think the big strength of this method that I'm talking about here lies in this region, in, you know, 10 to 100 MeV up to maybe a GeV. Beyond that, like you said, the electroweak radiation will make it so that, you know, the gamma ray limits are comparable to the neutrino limits. Yeah, so that's a great question.
Okay, thank you. Thank you very much.
Thank you.
Ibrahim.
Yes.
Did you mention some alerts about your the others experiments, and then you looking for this neutrino detection?
Mm-hmm.
How big is the data you need to process to really find an event?
Are you asking how long does it take, or
Yes. How long will you need
So the latency is less than a minute. So we have online filters at the South Pole, and if they see something interesting, it's sent directly via satellite. And in less than a minute after we see an event, the other telescopes will have the information.
Just in time.
Yeah. There's a lot of work that is put into. It's called real-time analysis, and there's a whole group that's dedicated to just making these algorithms faster.
Oh, okay.
Yeah.
That's down
Yeah.
in the IceCube is a digital optical model. It's a PMT or
yes, it's a 10-inch PMT. So it's about this big.
Okay.
And it has its own digitizers, and all it does is sends digital signals up. Yeah. So all the power is inside, and the data collection is inside. So each of these DOMs is its own detector, basically. And then they each send. They have timestamps, and they send all of the exactly what time they saw every hit, and then it's all put together in the lab once it gets up there.
Okay, but this face is put from the in direction of the ground or another director. The face of PMT.
Oh, the face, it's pointing down. Yes, it's pointing down.
Put in the ground.
Yeah, yes. And in the next iteration, so there's an IceCube upgrade coming, and there's a next Gen 2, it's called. We're trying to explore other configurations, because this was just an idea to say, hey, we just want to look through the Earth. But actually, after we turned it on, we found out that there's so much more science to be done, that the PMT facing down is actually limiting us. So the next iterations will have different configurations. So there's there's one pointing up and one pointing down, or there's smaller PMTs that are pointing everywhere in a circle or in a sphere. So they're being explored.
Okay. There's some question, guys. Okay, then, and we're talking. We thanks you again, and I asking for everybody turn on the microphone for applause. Vocês podem abrir os microfones para a gente fazer uma salva de palmas?
Congratulations. Thank you very much.
For you.
Thank you.
And nice work, nice presentation. It's very didactic. The slides is very well made. Thanks for you.
Thank you. I appreciate it. Thanks for the invitation. And like I said, if you have any other questions or you want to know anything about how it's like to work in IceCube, feel free to email me. I'll be happy to answer your questions.
Okay.
Thank you, everyone.
Thank you.
Okay.
Bye-bye.
Bye.